So yesterday we looked at graphing some rational functions where the degree in the bottom was bigger than the top. So maybe you had something like x squared plus 3x plus 2 divided by x cubed plus 4. Okay, so when we did that, the degree in the bottom was bigger. Or we looked at some where maybe the degrees were the same. The degree in the top is 2, the degree in the bottom is 2. That's what I just told you. So the degree of the numerator was always less than or equal to the denominator. Less than, equal. Now we're going to look at what happens if the degree of the number in the top is bigger than the bottom. Okay, so we're going to look at what happens when the numerator is greater than the denominator. Okay, so we're going to graph rational functions where the degree of the top is bigger than the bottom. Okay, so top one is what we did yesterday. Bottom one is what we're going to do today. Now, the bigger that the top gets, like the further apart that the top and bottom get, if you had something like this, let's say it's something like that. What's the highest degree term in the top?
x5. X power.
So the degree is
5.
5. And what's the degree of the bottom?
2.
2. And what's that a difference of? 3. The bigger that difference, the more complicated it is to graph. Right? We're only going to look at ones where there's a difference of 1. So maybe it's like a 5 in the top and a 4 in the bottom. Or a 3 in the top and a 2 in the bottom. Okay? If it's a difference of 1, that's a lot easier to draw. Okay? That would be pretty complicated to do. All right, so when the degree in the top is bigger, there's something new that well, it's not really new how we find it, but it's new what we're calling it. It's called the EBA, the end behavior asymptote. The end behavior asymptote is only something you can do when the degree in the top is bigger. Yesterday, we never had a problem where the degree in the top was bigger, so we never talked about this because you can't do it. So let's say we had two polynomials. Okay, they could be something like I have in red right there. But you have two polynomials, and you're going to divide them. And the degree of the top is bigger than the degree of the bottom. To find the EBA, this is how you do it. And it's something you already know how to do. When you divide two things, what do you call the answer when you divide two things?
Quotient.
The quotient, and then the part that's left over
Remainder.
is the remainder. So when you divide those two things, you're going to get a quotient. I'll just call it Q of x. And you're going to get a remainder. The only part that we really care about is Q of x. After you do the division, you're going to get a quotient and a remainder. Q of x is the EBA. So finding the EBA is something we already know how to do. We just have to do long division. We're just going to call the quotient, instead of calling it quotient, we're going to call it the EBA, the end behavior asymptote. Okay, and just to kind of be clear what the EBA is, this takes the place of the horizontal asymptote. You will never have a horizontal asymptote when the degree in the top is bigger than the bottom. It's impossible. So this takes the place of the horizontal. Any question on that idea? You can never have a horizontal when the degree in the top is bigger than the bottom. All right, so let's take this problem. I know I said to you we're only going to focus on ones where the degree in the top is 1 away from the degree in the bottom. This one is 2 away. But we're not going to graph. Okay? All we're going to do is find the quotient, the remainder, and the EVA. Okay, we will not be graphing it. That's the part we're going to skip for this one. Okay, so if I want to divide it, start with x minus 2 on the outside. And what would I put on the inside? And we have to make sure we put in zeros for any term we're missing. Yep.
2x cubed minus 4x squared, and then plus 0x.
Yep.
Plus 3.
Plus 3. All right, let's do this out. And then once we do it, we'll have the answer to all 3 of those things. Quotient, remainder, and EVA. Okay. First one is 2x cubed divided by x. What's 2x cubed divided by x? 2x squared. Yep, 2x squared. Okay. Now remember, you take and you multiply that back out. So 2x squared times x is 2x cubed. What's 2x squared times negative 2? Yep.
Negative 4x squared.
Negative 4x squared. And anybody remember what we do with the columns? Yep.
Subtract the negative.
Yep. We're going to subtract the columns. Okay. Isaiah, what's 2x cubed minus 2x cubed?
0.
Okay. That should always disappear. And Lily Rose, what's negative 4x squared minus negative 4x squared? 0. That cancels too. There's not really a lot left to do here. Bring down your next term. How many times does x go into 0x? 0. Doesn't go in at all. Multiply the 0 back out. What's 0 times x?
0.
0. 0x. And what's 0 times negative 2?
0.
0. Yes, I could just bring down the 3 to make that closer so when we do it, it looks a little simpler. And now subtract. Basically just subtracting 0. 0 minus 0?
0.
3 minus 0.
3.
That's it. Okay, so let's write down what they want to know. Okay, quotient. What's the quotient there? Yeah.
2x squared.
Yeah, we don't have to write plus 0. You just say 2x squared. What's the remainder?
3.
3. And what is the end behavior asymptote?
It's just 2x squared over 1. Or just 2x squared.
Yeah, just 2x squared. The quotient is the EVA. They're the same thing. So it's just 2x squared. And that's it. That's the quotient, the remainder, and the EVA. Any question on that? So I'm going to graph that, and let me show you something. All right, let's put in the original problem. Let's put that in y1. So let's put in 2x cubed minus 4x squared plus 3, and then divide by x minus 2. Okay. I'm going to set, I just know what's going to happen here. I need to set my y max higher. Let's set the y max at like, let's try 30. I don't remember if that's high enough, but let's see. Okay. The other thing I'm going to do is in y2, I'm going to put the EBA. It was 2x, what was it, 2x squared?
Yeah.
And you don't have to do it this way, but I want to do it. I want to make it a thin dotted line. Again, you don't have to. I just want to because the thinner I make it, the easier it's going to be to show you something. To make it a dotted line, I can highlight the color, hit enter, and then I can do a couple things. I can change the color, or I can press the down arrow, and then I can change what kind of line it is. I want it to be a thin dotted line. And then I have to press OK. And now you can see it showing it as a thin dotted line. Let me graph that and see if I set my window right. Yep, I did. So that's the original. And this dotted line that you're starting to see, that's the end behavior asymptote. Okay. What do you notice about the red dotted line and the blue line as you head up and to the right? Yeah?
The blue seems to make a parabola of the red one.
Yeah, so the blue one, basically, it's like a parabola that somebody cut in the middle and then broke the two pieces off and then bent them the other way. So it's like it could have been a parabola, but it was cut and then bent apart. And now look at the red dots and look at the blue curve. What do you notice as you keep heading up and to the right?
You're still in the same direction?
Okay.
Like we're on top of each other?
Yes. Let me do it this way. Let me make this. Let me make that a thin line, and let's make the red one a solid thin line. Maybe that'll be better. So, okay. Let's grab it. Yeah, I think maybe the solid line would be better. Okay, but I made it thin. All right, yeah, I think that's actually better. Let's look at it now. Okay, so what do you notice as you head up and to the right between the blue and the red? What happens, yeah?
Seems like they're converging and making one solid line.
Yeah, they're getting closer and closer together. So remember we had, in the last section, we had horizontal asymptotes, and then we had graphs that maybe did something like this. Right? They got closer and closer and closer to that dotted line, but did they ever touch the dotted line? Okay. So we had something that was straight, that the graph was getting closer and closer to. This is something that is curved, that the graph is getting closer and closer to. So it's a curved, the red thing is a curved shape, and the blue one gets closer and closer and closer to the red one over time. So that's called an end behavior asymptote. More complicated than a horizontal. That's why we're not sketching it. I just want you to see that the red and the blue get closer and closer and closer. Any question on how they're getting closer and closer? So you don't have to sketch it. You would just have to know how to find the red thing. So I might ask you, what is the blue graph getting closer and closer to over time? All you'd have to do is find the EDA, and that's with long division. Any question on the long division? All right. So, a couple important points. There's a difference between the end behavior asymptote and the end behavior model. The end behavior asymptote, you use long division. The end behavior model, that's easier. You just take the highest degree term in the top and you divide by the highest degree term on the bottom. That's a lot easier. Okay, so end behavior model is what we did yesterday. Sometimes the EBM and the EBA are the same, sometimes they're different. It depends on the problem. So EBM, highest degree term in the top, divided by highest degree term in the bottom. EBA, long division. But they could come out the same depending on the problem. Okay. What were the two kinds of asymptotes that we learned about yesterday? Yeah?
Vertical and horizontal.
Vertical and horizontal. And those are both examples of what kind of shape?
Say it again.
You said, well, vertical, can you be more specific? Vertical and horizontal
Asymptotes.
asymptotes. And what shape are they?
Straight lines.
Straight lines, exactly. That's the key word right there, straight. The kind of asymptotes we learned about yesterday were straight. Today, when the degree of the numerator is not smaller, when the degree of the numerator is bigger, the asymptotes can start to curve. And that's what that red one was that I showed you. So when the degree in the top is smaller, you always get straight line asymptotes, verticals and horizontals. You can still get verticals today. Those don't go away. But the horizontals are going to go away. We're not going to have those today. I'm trying to scroll down for you, but it's not hard. You are not responsible for knowing how to sketch an asymptote that curves. I would just ask you to find the asymptote and tell me what it is. You don't have to sketch it. So let me go back. To that question for a second. Okay, what was the highest degree term in the top of f of x?
Actually, third.
Yep, so the highest degree here was the 3. What was the highest degree in the bottom?
1.
A 1. What's the difference between 3 and 1?
2.
2. And something that's a degree 2 has what shape to it?
Parabola.
It's a parabola. So if you look at the difference between those two numbers, that's going to tell you exactly what the exponent is on your end behavior asymptote. Those are only 2 apart, so you get a parabola. The one I'm going to have you guys graph, they're going to be 1 apart, not 2 apart. 1 apart is a little bit more complicated than yesterday, but not as complicated as a parabola. Okay, so we already verified what we found, so we're not going to graph that on the calculator again. Let's try this one. So it says to determine the end behavior asymptote, vertical asymptotes, and then sketch the graph. Okay, can you have a horizontal asymptote when the degree in the top is bigger? No. So you're not going to have a horizontal. That is going to take the place of it. Right, so how do you find the end behavior asymptote? What do you have to do?
Long division.
Yep, you have to do the long division. So we're going to put x squared plus 2x minus 3. And it looks like it could be kind of bad because there's 3 terms in the top, 3 terms in the bottom, but they're only 1 degree apart. So that's actually going to make it not that bad. Okay. So x squared plus 2x minus 3. And then 2x cubed plus 7x squared. And what do I need to put now because I'm missing something?
0.
Yep, plus 0x. That's just a placeholder. So if we get any x's, we put them in that spot. And then the last thing at the end?
Minus 4.
Minus 4. I'm going to move this, put this back after. All right, so take first term. We'll do that. Take the first term on the inside and divide by the first term on the outside. 2x cubed. And we're going to divide by x squared. Okay, what do you got? 2x. Yep. So 2x. All right. Now, what do we do? Well, Lance, what do we do with that 2x?
Which 2x?
This 2x.
Oh, you distribute it?
Yep. I'm going to distribute it back out. So, Raina, what's 2x times x squared?
2x cubed.
Perfect. Brady, what's 2x times 2x?
Would it be 4x squared?
4x squared. And Cam, what's 2x times negative 3?
2x times -3 is -6x.
Okay, and now, Alex, we're going to take these columns, and what do we do with them?
Subtract.
Yep. Subtract them. 2x cubed minus 2x cubed is gone. Alex, what's 7x squared minus 4x squared?
3x squared.
We don't even really need the rest of it, because all we're interested in is the quotient. The rest of it would be for remainder. I'll do it, but we don't need it. What's 0x minus 6x?
6x.
6x. And then bring down your 4. So to finish the quotient off, all I care about is that divided by that. What's 3x squared divided by x squared? 3. So really, I can stop. The only reason I'd have to keep going is if I wanted the remainder. But that's not part of the EDA. You just need the quotient. So there's your EDA, 2x plus 3. Now, that's not as complicated as a parabola. It doesn't curve, but it's also not a horizontal line. What's y equals 2x plus 3? What is that going to look like?
A slanted line.
It's going to look like a slant. Yeah. And this is going to be called a slant asymptote. So this is the kind of asymptote you do have to know how to draw. So it's a little more complicated than horizontal, but it's not as bad as a curve because it's still straight. It's just on a slant. Okay, so this is called a slant asymptote. Okay. What's my y-intercept on my slant asymptote?
3.
3? I'm going to try to bring this back all on the same page. That works. Well, it's a 3. And what's my slope?
2 to 1.
2 over 1. So that means up to right 1. Yep. Yeah. Now remember, this is an asymptote. So how do we usually show that it's an asymptote?
Dotted line.
Yeah, we'll make it dotted. Okay, so when we draw our graph, we're going to have something that's getting closer and closer to that dotted line. Okay, so no horizontal. What other kind of asymptote should we check for?
Vertical.
Yeah, we always have to check for the verticals, and that's where the denominator would be 0. All right, so let's see if we set the denominator equal to 0. So this is the EBA. Right, and now we'll do the vertical asymptotes. Take the denominator, x squared plus 2x minus 3. Set it to 0. I could use quadratic formula, or what else can I do as long as the numbers work out?
Factoring.
Yeah, we can factor it. So we'll need an x and an x. What about my signs? Both positive, both negative, or one of each? Christian, what do you mean?
Negative and positive.
Yep, you're going to need one of each. And two numbers that multiply to give me 3.
1 and 3.
1 and 3. Yep. Let's check it. 3x minus 1x, 2x. Perfect. All right. So what would you plug in here to make that 0? Yep. That's a vertical asymptote. And what would you plug in here?
Negative 3.
Negative 3. So how many vertical asymptotes did I get? 2. So let's put one at 1 and one at negative 3. I'm just going to zoom out. It's a little easier if I do it that way. 1, negative 3. And what that does is it kind of divides the graph into different sections. And we usually end up drawing in 3 of them. It's usually like 1, 2, and 3. All right, so now the calculator is what's going to help us do the rest. We're going to use the table, and we'll just plot some points. All right, when I type that in, what symbol should I use to make sure the calculator does it correctly? Yeah,
Parentheses.
yeah, you got to put it in parentheses. So 2x cubed plus 7x squared minus 4, and then divide by x squared plus 2x minus 3. First thing we should check out is numbers near the vertical asymptotes. One usually ends up very low. On the other side, it ends up very high. What's a number that's a little bit smaller than negative 3? Yeah.
Negative 3.01.
Yeah, negative 3.01. We're up at 1,246.
Small numbers.
So yeah, that's up very high. So just to the left of negative 3, going to be way up. Let's check out just to the right. So what's a number a little bigger than negative 3?
Negative 2.99.
Yep, negative 2.99. And we're at negative 1,200. So way down there. Right. Our other vertical asymptote is at 1. What's a number that's a little bit smaller than 1? Don't do 1. You're going to get an error. Can't do that. But a little smaller than 1. Yep.
0.99.
All right. So just to the left of it, we're going to be at negative 1,200. So we're going to be down there. And where do you think if we go just to the right of it?
0.01.
Yeah, we're going to be up very high. 1 point. Keep hitting the decimal. We're up at like 1,200. All right, so I got a few points that kind of help me. Let's get another point that would be somewhere in this section. What would be another good x value we could pick?
3.5.
3.5.
Okay,
That,
negative 3.5.
yeah, we could do like negative 3.5. Yeah, let's try that. Because I still don't know what it looks like. All right, that I can do. Negative 3.5, about negative 2. So negative 1.7, so maybe right about there. All right, what would be another one I could do?
Negative 4.
Yeah, let's even move away from it a little more.
Negative 10.
Yeah, I can try negative 10. I think I'm going to be a little bit too low, though.
Negative 7.
Yeah, negative 7 might be the most I could fit. Yeah, just barely. So negative 7, negative 10. 1, 2, 3, 4, 5. Negative 1, 2, 3, 4, 5, 6, 7. That's, yeah, I really kind of going off my graph a little bit. All right, so I have an idea what this is doing. It's going to stay right up next to that. And then it's going to curve. And it's going to go through that point just like that. All right, so there's the left part. Let's try the middle part. Right now, I only have 2 dots. What's another x value I could test right in the middle?
Negative 1.
Yeah, we could try negative 1. Negative 1, I'm at negative 1/4. So negative 1, just barely below 0. Okay. What's another one I could check?
Negative 2. Or 0.
Yeah, I would check 0. 0, you're at 1.3. 0, just above that. Now I got 4 dots in the middle. I can kind of see what's going to happen here. It's got to stay close to this, but it can't keep going straight because it runs into that asymptote. And then it can't keep going up and to the right because it hits another one. And it's got to come back down and go through that one. So there's the middle. And now what would be a value we could check that would be somewhere over here?
Just 2.
2. Yeah, 2 would be a good one. So 2, 8 is a point. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Let's check 2.5. Let's go a little bit more. 2.5, we're up a little bit higher. So 2.5, 8.6, be about right there. I can kind of see what's happening here. This part is going to come down. It's going to curve. And it's going to go back up like that. So that's basically what your graph looks like. Let's see how we did. Let me do zoom 6. You're just barely going to see the top part of it. You're not going to see much at all on the top part because it's almost off the screen. There's the middle, and there's that little top part right there. Yeah, looks pretty good. Any question on that one? So really, once you get the horizontal, or once you get the vertical and the slant asymptote, it's just a matter of picking a bunch of points. I'd say maybe like 3 or 4 per section, and then that'll tell you what your graph is going to look like. Now that's probably the most complicated one we'll do because it had 2 vertical asymptotes. I'm going to finish with one that only has 1 vertical asymptote. And that'll be a little easier because with 1, it doesn't break the grid into as many pieces. Okay. Any question on that one? Let's, I don't want to do that one. All right, let me make one up. I don't want to do that one. Let's do, let's try f of x equals x squared plus 2x plus 5. I just have to make sure that's not factorable, or we're going to end up with a whole instead of an asymptote. I don't think it is. No. And let's try x plus 3. All right, so let's, what do we want to do? Graph. Okay, the top is bigger, so will you have a horizontal in this case? What do you think? No. When the top has a bigger exponent, you can't. You will not get a horizontal. So we're going to end up with an end behavior asymptote. How do you find the end behavior asymptote? Yep, and do you know how to find the EBA?
Yes. X over 1.
Not the end behavior model. The EBA is a little more complicated.
That's with long division.
Yeah, got to use long division. Yep. But again, notice I made it so the bottom one is a 1, the top one is a 2. They're only 1 apart. So you're going to get a slant. You're not going to get a curve. It's going to be a slant. Okay. What do you get when you divide x into x squared? Yep.
Just like X.
Just x. Multiply it back out. What's x times x?
X to the second.
X to the second. What's x times 3?
Yes.
3x. And what do we do with these columns? Subtract. X squared minus x squared is gone. What's 2x minus 3x? Negative 1x. You can bring down the 5, but it doesn't matter because we're not going for the remainder. What's x, or negative x, divided by x? Negative 1. There's your end behavior asymptote. It's y equals x minus 1.
Which is also the quotient, right?
Which is the quotient. Yep. Okay, so that's the EBA. Now let's find the vertical asymptote. Vertical asymptote is when you set the denominator equal to 0. This time I made the denominator a little simpler. What do you get for x when you set the denominator equal to 0? Negative 3. That's it. So we have 1 vertical and 1 slant. Okay, let's sketch it and see what it looks like. Put that there. There. All right. What's my y-intercept on the EBA?
Negative 1.
Negative 1. So that's my y-intercept. And what's my slope?
Over 1.
1 over 1. So where do I go from my y-intercept to get another point?
Up 1.
Up 1 in which way?
Over 1, right.
Right. Up 1, right 1. And rather than make it a dotted line, I'm just going to do that a bunch of times. That's good enough. So that's my slant asymptote. Where's my vertical asymptote? What number?
Negative 3.
It's at negative 3. That one I'll just do it like this. Now, in this type of graph, it's almost like an X shape. And you usually end up drawing in 2 of the sections, not 3. This one's a little easier. All right, let's type that in, and the calculator is going to help us figure out some points. To type it in, what do I have to make sure I use? Got to use parentheses. X squared plus 2x plus 5. And we're going to divide by x plus 3. Okay, first thing I want to do is check near my vertical asymptote, negative 3. What's a number? You don't have to delete these, I just am, so you don't get confused with other numbers. What's a number that's a little smaller than negative 3? Yep.
3.01 or 001.
Can you say it again?
3.001.
Smaller than negative 3.
Negative 3.001.
Negative 3.001. we're at negative 8,000. So we're basically way down. Okay, so there's negative 8,000. It's off the graph. All right. Let's try a value a little bigger. What's a number that's a little bigger than negative 3?
Negative 2.99.
And where do you think I'm going to be when I hit enter?
Really high.
Really high. Yeah, we're up at 80,000. Okay, so right here, way off the graph at 80,000. Okay, now, we just need some more points to see what's happening in this section and then what's happening in that section. Let's start with the lower left. What's an x value that would be in the lower left area?
-6.
Yep, we can do negative 6. So negative 6, negative 10, roughly. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so right about there. What's another x value?
-4.
Yeah, let's say negative 4 is a good one. Negative 13. All right, so negative 4. All right, I'm basically like, well, that'd be negative 10. Negative 13 would be even lower. All right, let's try one like, well, kind of see what's happening. This is going to have to stay near that. That is going to get closer and closer to that dotted one. Those are going to get closer. And these two pieces have to connect. So I don't know exactly how high it's going to go, but I'm guessing it's going to be something kind of like, I didn't draw it perfect, kind of like that. And then these get closer and closer and closer. So this should look a little straighter. Something, that section looks something like that. All right, what would be a good x value for the top one?
-2.
Yep, do negative 2. So 5, that one I can do. 2, 1, 2, 3, 4, 5. Okay, what would be another one?
-1.
All right, negative 1, 2. Okay, how about another one?
0.
Yep, 0. Kind of want to get further to the right. So 0, 1.6. Let's try like 1, 2, 3, 4. Let's try 5. 5, 5, 5. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so what's happening here? It's kind of coming down. It's curving. And then it's going to get closer and closer and closer to that dotted line. Alright, so that's what I think it should look like. Let's see. Well, if I set my Y min a little bit lower, you'll probably see it better. Negative 25. And yeah, it's basically what it looks like. You get that piece in the lower left, and then that upper piece in the upper right that just kind of continues off in it. All right, so that's probably one similar to what you'd see on the test because it only has one vertical instead of 2. All right, any question on finding the EDA or the vertical asymptote? All right, so let me put up, that's the homework for tonight. Okay, I'm going to pause it, and then I'll also put a list of topics that are going to be on the test.
The test is tomorrow, right?
Yes, the test is tomorrow because we have a half day on Friday.